most people don't really know what time is. We count it with clocks and calendars, but that's just numbers. That's not time itself. That's like using a thermometer and thinking you understand heat. Time is stranger than we've been told, and far more powerful. In this journey, we'll pull back the curtain. First, we'll ask a fundamental question. What is time really? Is it a flow, a direction, or something else entirely? Then, we'll go faster. We'll look at how you might leap into the future, not in theory, but in reality. Scientists already know how to do it. The challenge is scale and speed. But where it gets wild is the past. Can we go back? Can we visit a moment that's already happened? Some believe wormholes could make it possible. Others think of paradoxes that could destroy everything. And finally, we'll arrive at the moment where time itself begins to unravel. Where logic bends, physics trembles, and all the familiar rules of reality break down. It's at this edge of chaos and brilliance that we dare to build a time machine. Not just imagine it, but truly understand how it might work. So take a closer look at your clock, because by the end of this video, you'll never hear it the same way again. Like a river, carrying us along in a constant forward motion. But have you ever wondered what time actually is? Is it just a way we measure the past, present, and future? Or is it something much deeper? Something embedded in the fabric of the universe itself? At first, time seems straightforward. It's what clocks measure, what calendars track. We wake up in the morning, go through our day, and go to bed at night, all according to the ticking of the clock. You know it's 3:15 p.m. when you check your watch, and you plan to meet your friends next Tuesday. Time is the structure we rely on for everyday life. But the more scientists study time, the more complicated it gets. One of the first things that modern physics teaches us is that time is not a separate entity, something that just ticks away independently. Time is deeply connected to space. Space and time are not separate dimensions, but rather a unified entity. Imagine space as a vast, invisible sheet, stretching endlessly in every direction. Not a physical sheet you can touch, but a smooth, silent fabric that holds everything in the universe. Stars, planets, galaxies, and even the light that travels between them. Now, imagine that this fabric doesn't just represent space, but time as well. Together, they form what scientists call space-time, a single, unified structure that makes up the very foundation of the universe. This concept might sound abstract at first. After all, we usually think of space and time as completely different things. Space is where things are. Left, right, up, down, near, far. Time is when things happen. Morning, evening, yesterday, tomorrow. But in reality, these are not separate. They are two aspects of one deeper reality, woven together like threads in the same cloth. space-time was first developed in the early 20th century, and it marked a huge turning point in how scientists understood the universe. Before that, space and time were treated as separate and absolute. Time was thought to tick at the same rate for everyone, everywhere, no matter what. Space was seen as a fixed stage on which the drama of the universe played out. Then Albert Einstein came along and completely changed the picture. In his theory of general relativity, Einstein proposed that space and time are not fixed. They are dynamic and flexible. Space-time can stretch, compress, bend, and even ripple. It responds to the presence of matter and energy. In fact, gravity itself isn't a force in the traditional sense. It's the result of space-time being curved by mass. This is a truly radical idea, and to appreciate it, it helps to return to the image of a stretched fabric. Imagine laying a rubber sheet flat across a table. This is your space-time. Now place a heavy rolling ball in the center of the sheet. The fabric dips under the weight. This is what happens when you put something massive, like a planet or a star, into space-time. The surrounding area curves around it. Now, if you were to roll a small ball across the sheet, it would curve toward the heavier ball. Not because there's a rope pulling it in, but because it's following the curved path created by the dip in the fabric. That's how Einstein saw gravity. Massive objects bend space-time, and other objects move through this curved space in what we perceive as gravitational attraction. It's not a force in the traditional sense, but a result of the geometry of space-time itself. In fact, it's not just that the massive object pulls the smaller one. The smaller object is also pushed by the warped space-time around it, nudged along the curves that lead it toward the bigger mass. And this bending doesn't just affect space, because space and time are part of the same structure. When space is curved, time is curved as well. The same fabric that dips under the weight of a star also stretches the timeline passing through it. Time, in Einstein's model, is not something that flows at a fixed rate. It has no single rhythm for the entire universe. It is shaped by the same conditions that shape space. But here's where it gets even more curious. In Einstein's relativity, time doesn't have built-in labels like past, present, or future. These are words we use to describe our experience, but they don't exist in the physics itself. The equations of general relativity don't say, this is the past, or this is the future. They simply describe how time behaves, how it stretches and curves alongside space. Einstein's model treats time as a dimension, just like the 3 dimensions of space. You can describe a place by saying it's 5 meters north, 3 meters south, and 10 meters east. In space-time, you add a 4th coordinate, when. All 4 together, 3 in space, 1 in time, define where and when something is in the universe. But while space can be freely moved through in any direction, in our everyday experience, time appears to have a stricter path. We live in one moment and move to the next. And yet, in the mathematics of general relativity, all points in time seem to simply exist. The theory doesn't tell us which moment is now. It doesn't prefer the present over the past or the future. It just lays out the structure of space-time, all at once. This leads to a strange and subtle idea. Maybe time doesn't Just as all places exist in space, maybe all moments exist in time. We only experience them one at a time, but they're all already there, woven into the fabric of the universe. Einstein himself once said, "The distinction between past, present, and future is only a stubbornly persistent illusion." He didn't mean that time isn't real, but rather that our experience of its flow might be something our minds create, not something built into the laws of nature. But if that's true, why do we remember the past, but not the future? Why do broken cups stay broken and never jump back together? Why does time feel like it's always moving forward? If physics doesn't prefer one moment over another, where does this sense of direction come from? This is the classic arrow of time problem in Einstein's equation. While Einstein's equations treat time as just another coordinate, no more special than left or right, our everyday experience insists that time has a clear direction. It flows from what was to what is, and never the other way around. We are born, we grow older, and eventually we die. We light a match, it burns down to ashes, and we can't reverse it. There's something deeply one-way about the world we live in. To explain this, scientists look not to gravity or relativity, but to thermodynamics, the science of heat and energy. In particular, they look to the second law of thermodynamics, which says that in a closed system, entropy, the amount of disorder, always increases over time. It's a rule of nature. Things naturally go from ordered to messy, from neat to scrambled. Let's say you drop an egg on the floor. It breaks. The shell shatters. The yolk rolls. That's entropy increasing. It's incredibly unlikely that all the broken pieces and liquid parts will just leak back into your hand and reform the egg. Not impossible in theory, but so improbable that it just doesn't happen in reality. That direction, from order to disorder, is what gives time its arrow. Entropy doesn't just apply to eggs. It applies to everything, from stars burning out, to ice melting, to the expansion of the universe itself. Every system moves toward more disorder, and this increase in entropy gives us a sense of before and after. It gives time a direction, even though the fundamental laws of physics don't. You can think of it like reading a book. The words on page 10 are no more real than those on page 50. They all exist in the book at once, but we read from front to back. In the same way, all moments exist in the universe's space-time book, but entropy makes us experience them in one direction. Interestingly, if you were to film the egg falling and play it backwards, it would look strange. Not just because it's unfamiliar, but because it violates this deep rule about increasing entropy. That's why we can tell if a video is playing forward or backward. We recognize the arrow of time. Now here's where things get even more curious. The laws of physics don't actually say the egg can't unbreak. They just say it's so incredibly unlikely that it won't. The equations work just as well in reverse. That means the direction of time isn't built into the equations. It comes from how things are arranged and from the strange way entropy works. So time, as we experience it, feels like a one-way street. But under the surface, the rules that govern the universe are more flexible. The present is not as unique as we think. far behind us after all. But to go deeper into those possibilities, we'll have to ask a much bigger question. If time can bend, and entropy gives it direction, is there any way to travel through it? When Russian cosmonaut Sergei Krikalev returned to Earth in October 2005, he wasn't just any astronaut coming home. He was the most experienced space traveler of his time. Over the span of nearly 2 decades, Krikalev flew on 6 separate space missions, logging a total of 803 days, 9 hours, and 39 minutes in space. That's more than 2 full years spent orbiting above Earth, watching sunrises and sunsets pass by the windows of space stations faster than anyone on the ground could imagine. His career began during the Cold War era, when he launched aboard the Soviet Soyuz TM-7 mission in 1988. He worked on the Mir space station, which at the time was the crown jewel of Soviet space exploration. Krikalev returned to Mir spacecraft multiple times, living and working in microgravity under challenging conditions, often for months at a time. He was known for his calm under pressure, technical skill, and willingness to spend long durations far from home. In fact, during one mission in 1991, the Soviet Union dissolved while he was in orbit, leaving him in the odd position of being a citizen of a country that no longer existed. Later, as the space era shifted from competition to cooperation, Krikalev joined NASA astronauts aboard the space shuttle and eventually became a core part of the International Space Station program. He flew the first expedition to the International Space Station in 2000, and later returned for a 6th mission in 2005, this time as a seasoned veteran. That final trip pushed his total time in space past 800 days, setting a world record at the time. Across those missions, Krikalev experienced life in space in a way few humans ever have. Floating, working, sleeping, and even celebrating holidays hundreds of kilometers above Earth. And with each passing mission, he became more than just a space traveler. He was technically a time traveler to the future. Yes, you heard that right. And here's why. When Krikalev was in the space station, he was moving incredibly fast. About 7.66 kilometers per second, roughly 27,600 kilometers per hour. According to Einstein's special relativity, the faster you move, the slower time passes for you compared to someone standing still. So, while Krikalev was orbiting Earth, his body and his onboard clock were experiencing time a little more slowly than those on the ground. That means, while 1 second passed for us, slightly less than 1 second passed for him. It's a tiny difference, yes, but it's real. Over his 803 days in space, this added up to about 20 milliseconds, a tiny fraction of a second, but enough to say that when he landed, he was that much younger than he would have been had he stayed on Earth. This difference in aging means that Krikalev literally moved forward through time, just a little bit more slowly than the rest of us. So when he returned, he was technically in the future, compared to where he would have been if he'd never left. He didn't go forward in time faster than us. We moved faster than him in time. In Einstein's theory of special relativity, the faster you go, the slower time moves for you compared to someone who's staying still. This is called time dilation, and it's a real effect confirmed again placed in a fast-moving satellite orbiting the planet. After a while, when you bring them back together and compare them, the clock that traveled will have fallen a tiny bit behind. This is not just a theory. It's been tested using actual atomic clocks, flown in military planes and commercial satellites. In one famous test in 1971, physicists Joseph Haffel and Richard Keating flew 4 atomic clocks around the world on commercial jets. When compared with clocks that stayed on the ground, the flying ones had lost time, just like Einstein predicted. The equation that explains this is called the time dilation formula. It comes from Einstein's special relativity and looks like this. Don't worry about solving it, just understand what it means. Here, t is the time that passes for someone moving at speed, denoted by v. T is the time that passes for someone at rest, and c is the speed of light. As v, the speed you're moving, gets closer to c, the speed of light, the number under the square root gets smaller. That means the whole expression becomes bigger, meaning your time slows down more and more. In everyday life, we don't notice this effect because we're all moving relatively slowly compared to the speed of light. But in space, things change. A spacecraft orbiting Earth travels at about 28,000 kilometers per hour. That's fast enough to make a difference, even if it's just milliseconds over months. But if we could somehow move with the speed of light, the effect would be dramatic. Imagine boarding a spaceship and traveling at 99.9% the speed of light. You go on a long journey, flying through space for what feels like a year to you. But when you return to Earth, decades have passed here. Everyone you knew would be older, maybe even long gone. From your point of view, you only aged a year. But from Earth's point of view, you skipped far ahead into the future. Your own clock slowed down so much that you leapt through time without feeling anything unusual. Here's another way to look at it. Think of everyone on Earth watching a movie at normal speed. Now imagine you're watching that same movie, but in slow motion. The longer you watch, the more out of sync you become. Eventually, when the movie ends for them, you're still halfway through. That's what it's like when you're moving near light speed. Your time moves slowly, while the rest of the universe moves quickly around you. But speed isn't the only thing that affects time. Gravity plays a huge role too, and not in the way you'd expect. According to Einstein's other great insight, general relativity, gravity isn't just a force. It's actually the bending of space-time itself. The more massive something is, like a planet or a star, the more it warps the space and time around it. And the closer you are to that massive object, the slower time flows for you. This is known as gravitational time dilation, and it's one of the wildest parts of Einstein's theory. A great way to picture this is through a powerful scene in the movie Interstellar. In the film, the crew of the spaceship Endurance heads toward a monstrous black hole named Gargantua. They land on a planet that orbits dangerously close to it, so close that the black hole's gravity is stretching space-time to the extreme. On this planet, time is barely moving compared to Earth. For every hour they spend on the surface, 7 whole years pass back home. It sounds impossible, but that's what happens when gravity is that strong. It warps time itself. The scene gets even more emotional when the crew finally returns to their ship. To them, only a few hours have gone by, but when they step back on board, One of their crewmates, who stayed behind on the ship, is now 23 years older. He waited, alone, for over 2 decades, all because they were that close to a black hole where time was crawling. This scene is a vivid illustration of how gravity, especially near extremely massive objects like black holes, can distort time. The closer you are to a massive object like Gargantua, the more space-time is stretched, causing time to move much slower for you. Christopher Nolan, the director of the film, didn't just make this up for dramatic effect. The concept of gravitational time dilation near a black hole is grounded in real physics. Kip Thorne, a theoretical physicist and Nobel laureate, worked as a scientific advisor for the film. He ensured that the depiction of Gargantua and the planet was scientifically accurate. Thorne's work with general relativity provided the basis for how time behaves near such a massive object. But while this might seem like a fantastical scenario, gravitational time dilation is something we can observe in much smaller, everyday situations. The effects are just far less dramatic than in the movie with the massive black hole. In the 1970s, scientists tested the effects of gravity on time by sending 2 highly accurate atomic clocks to different altitudes. One clock was placed at sea level, and the other was taken up to the top of a mountain, about 2,300 meters, or 7,500 feet, above sea level. After 11 days, the 2 clocks were compared, and scientists found that the clock on the mountain had ticked slightly faster than the clock at sea level. This is a direct result of gravitational time dilation. The reason this happened is that the clock at the top of the mountain was farther away from the center of Earth's gravity. The higher you go, the weaker the gravitational field becomes, and so the less it warps space-time. Because of this, time passes slightly faster the higher you are above the Earth's surface. On the other hand, the clock at sea level was closer to the Earth's mass, meaning time passed slightly slower there. The difference between the 2 clocks was incredibly small, only a few billionths of a second, but it was measurable with the technology available at the time. Other than traveling at lightning speed or being near a massive black hole, there's another intriguing way to travel into the future. The concept of a warp bubble. In 1994, physicist Miguel Alcubierre proposed a theoretical idea called the Alcubierre drive, and it turned a lot of heads in the scientific world. Using the math of general relativity, Alcubierre showed that if you shaped space-time in the right way, specifically by adjusting the space-time metric, you could create a region where space was moving faster than light, relative to the outside universe. Inside the bubble, time would pass normally for the travelers. Outside, however, the ship could cover distances that would take light thousands of years to cross, all in what feels like a short trip to the people inside. In other words, what if instead of moving a spaceship faster and faster through space, you move the space around the spaceship instead? Normally, when we think about traveling, we think about pushing through space, like a car driving down a highway. But in Einstein's general relativity, space and time are not just empty backgrounds where things happen. They're more like a flexible fabric, something that can stretch, bend, and even ripple. If you could control that fabric, you wouldn't have to move through space in the normal way at all. You could just ride a piece of space that itself is moving. Alcubierre's big idea was to create space would contract. Behind the bubble, space would expand. The spacecraft inside would stay perfectly still relative to the space around it, not moving at all, but the bubble itself would surf across the universe. Because the ship isn't technically moving through space, it could, in theory, travel faster than light without breaking any physical rules. Think of it like surfing. That's basically what the Alcubierre drive suggests doing, grabbing space-time itself and reshaping it to carry you across huge distances and through time as well. This isn't just about traveling faster than light, it's about traveling into the future. Here's how. Because time behaves differently inside a warp bubble, you could experience only a few months or years, while outside the bubble, centuries could pass. Imagine leaving Earth in 2100 and arriving at another star in what feels like 1 year to you, only to find that Earth's calendar says 3100. You would have effectively jumped 1,000 years into the future while only aging 1 year yourself. Another important detail is how passengers inside the warp bubble would experience the journey. Since they wouldn't be moving through space in the normal way, they wouldn't feel any acceleration at all. No crushing G-forces. No need for massive shields against interstellar dust. At least in theory. They would simply float along peacefully, while the universe outside raced by at incredible speed. But to actually make this happen though, you'd need something called negative energy, or exotic matter. This kind of energy would have to behave the opposite of normal mass and energy. It would create repulsive gravity instead of attractive gravity. So far, negative energy is purely theoretical. We know it can exist in tiny amounts in quantum fields, like in the Casimir effect, but we've never been able to create or collect it in usable amounts. However, NASA's EagleWorks laboratory took this idea seriously enough to study it. Dr. Harold Sully White proposed tweaks to the original model that would theoretically reduce the amount of negative energy needed. Instead of needing something like the mass energy of Jupiter to create a bubble, his modifications suggested that it might be doable with the mass of a car. Still a long shot, but far less impossible than before. Of course, the problems are huge. Creating the bubble would require manipulating space-time on a scale we don't know how to control. Even if we could make it, keeping the bubble stable without it collapsing or radiating deadly energy would be another massive challenge. Some theoretical work suggests that warp bubbles could accumulate enormous amounts of quantum radiation. If the bubble popped, it could release that radiation in a blast that would destroy the ship and anything nearby. But even with all these challenges, the Alcubierre drive stands out because it doesn't require rewriting the law of physics. It fits neatly within general relativity. It's just that the practical obstacles are, for now, way beyond our abilities. Another idea for traveling into the future involves a white hole. If black holes are famous for sucking everything in and letting nothing escape, white holes are the complete opposite. Instead of pulling things inward, a white hole would spit matter and energy outward. You can think of it like a cosmic fountain, blasting stuff into space instead of swallowing it. The idea of a white hole actually comes straight from the math of general relativity. When scientists solved Einstein's equations for black holes, they noticed that, in theory, there could also be a solution that looked like a black hole flipped inside out. Instead of an object you fall into and never escape from, this flipped version would be an object you could are a few theories that try to link white holes to some of the mysteries we see in space. For example, some researchers have suggested that short bursts of high-energy light, called gamma-ray bursts, could be white holes firing off energy, but so far, no solid proof. Still, the idea is fascinating. If white holes do exist, and if we could somehow reach one and survive the insane forces near it, we might be able to use it to catapult ourselves into the far future. It would be like finding a hidden shortcut across time itself, a cosmic cannon that blasts you out into another era. Another way to travel into the future, and this one feels a bit like Funny One, is to simply freeze yourself and wait it out. Instead of speeding up time or bending space-time with some wild cosmic trick, you could just hit pause on your own body and skip ahead to a later time. It's called cryonics. And while it sounds funny, it's an idea real people have actually tried. The basic idea is pretty simple. If you could somehow stop all the biological processes in your body without killing yourself, you could basically sleep through decades, centuries, or even longer. When the world has changed, maybe when we've cured all diseases, solved aging, or invented spaceships that can hop between galaxies, you could be thawed out, good as new, and start living again in a future era. Cryonics companies today actually offer this service. When a person legally dies, these companies quickly cool the body down to an incredibly low temperature, around minus 196 degrees Celsius, using liquid nitrogen. The idea is to freeze everything in place, from your brain cells to your organs, before too much damage happens. Then, they store you in a metal tank, and you basically just wait. Probably the most famous person to undergo cryonics is James Bedford, a psychology professor who died in 1967. He became the first person to be frozen this way, and technically, he's still out there, preserved in a cryonic storage facility. More people have followed since then, some choosing to freeze just their heads, hoping future science can regrow the body, and others choosing full body preservation. Of course, there's a big catch. As of right now, we have absolutely no idea how to bring a human back from cryonic freezing. Ice crystals can form and shred your cells. The chemical preservatives used can cause their own damage. Even if you're perfectly frozen, thawing you out safely is a gigantic challenge we haven't cracked yet. So freezing yourself is kind of like buying a very, very long lottery ticket. You're betting that future humans will figure it out. But in theory, if it ever does work, cryonics would be a true form of one-way time travel, except it's not your surroundings moving forward faster, it's you who stops moving while the world races ahead. If you went into cryonic suspension today and woke up in, say, the year 2500, you would have skipped over everything that happened in between. For you, no time would have passed at all. One moment you're here, the next, you're hundreds of years in the future, blinking at a completely new world. Still, it's fascinating to think about. Without needing to warp space-time or build impossible machines, cryonics gives a very different, very human way to attempt future travel. It might not be as flashy as riding a warp bubble or jumping through a white hole, but in some ways, it's even more daring. It's a bet that science, technology, and maybe a little bit of luck will catch up to your dreams of seeing the future. Of all the methods we've talked about, odds of success are slim. It's an experiment in hope. A gamble that the future will not only be incredible, but that it will find a way to bring you back to life to see it. Skipping forward in time is tricky enough. But what about going the other way? What if you wanted to rewind the clock and visit the past? It sounds impossible. Yet when you dive deep into the strange world of physics, you'll find hints that it's something that could become a reality. One of the most iconic moments in movie history happens when Marty McFly jumps into the DeLorean and hits 88 miles per hour. In Back to the Future, this is the magic number. The speed where the flux capacitor kicks in, the DeLorean sparks with blinding light, and in an instant, Marty is ripped out of 1985 and dropped into 1955. Fire trails streak behind the car, the scenery shifts, and without warning, Marty finds himself staring at a world that looks strangely familiar, but completely different. That idea, hopping into a car, hitting a certain speed, and zipping back into a different year, makes time travel feel thrilling and almost normal, like taking a trip to a new city. Of course, in reality, it's not so simple. But the basic dream that Back to the Future taps into is something physicists have seriously considered. Could there be a way to actually step backward through time? Could time be treated like space, where if you just find the right path, you could move not just forward, but also back? The real-world ideas for time travel to the past are much trickier and way more complicated than traveling to the future. But believe it or not, general relativity, the same theory that explains gravity and black holes, actually allows for some crazy possibilities. One of the most interesting ideas is the concept of wormholes. Hidden tunnels through the fabric of space-time that could connect distant points, not just across space, but also across time. Now, if Back to the Future made time travel look easy and fun, but as exciting as that idea is, the movie never really explained how it could happen in real physics terms. It was more about adventure than reality. Interstellar took a different path. The movie still plays with incredible ideas, but the physics behind it is much more grounded in real science. The scene toward the end of Interstellar that's unforgettable, where Cooper falls into the black hole called Gargantua. Earlier in the movie, we saw an example of how gravity could push someone into the future. When Cooper and his crew landed on the water planet near the black hole Gargantua, time passed differently for them compared to people farther away. Just a few hours on the surface of that planet equaled more than 20 years back on the ship. By the time Cooper and Brand returned, their crewmate Romilly had aged decades, while they had only aged a few hours. Cooper didn't build a time machine. He didn't use any special device. Just by being close to Gargantua's powerful gravity, he had jumped into the future compared to everyone else. But the real mind-bending part came later, when Cooper let himself fall into Gargantua to give the Endurance a chance to escape. He didn't just experience extreme time dilation, he went somewhere stranger. Instead of being crushed by the black hole's unimaginable forces, he ended up inside the Tesseract, a strange, higher-dimensional space where every moment in his daughter's childhood bedroom existed at once. Time wasn't versions of the room, layered like a deck of cards, stretched across dimensions. In that moment, Cooper wasn't just traveling through time, he was shaping it. And because his daughter solved the equation, future humans created the Tesseract and sent it back to save them. A perfect loop across time. What's really fascinating here is that Cooper didn't break the past or create a paradox. He didn't change history in the sense of creating a new timeline. Instead, everything he did inside the Tesseract had already happened. He was always the one sending those messages. He just didn't know it until he was inside the Tesseract. The future and the past were tangled together in a way that made everything consistent. This idea lines up with a concept in physics called a closed time-like curve, which we'll elaborate later in the video, where time loops back on itself and events are self-consistent. It's strange to think about, but it means that the future and the past can influence each other without breaking the rules of cause and effect. Cooper's actions in the Tesseract show us a version of time travel that doesn't destroy the timeline, it fulfills it. While Cooper didn't physically travel back to the past, he did influence it from the Tesseract. He reached across time without truly stepping into it. But is full travel into the past, actually moving your whole body back in time, possible? Surprisingly, physics says yes, through something called a wormhole. In theory, a wormhole is a shortcut through space-time. Instead of traveling across the long, flat surface of space, you could slip through a tunnel and pop out somewhere far away, or maybe even somewhere else. Imagine the universe as a giant piece of paper. If you wanted to travel from one side to the other, you'd usually have to move across the sheet. But what if you folded the paper and poked a hole through it? Suddenly, two distant points would be touching, and you could jump from one place to the other in no time. That's the basic idea of a wormhole. Physicists call this a solution to the Einstein field equations known as an Einstein-Rosen bridge. It's like a bridge connecting 2 points in space-time, and depending on how you set it up, it can let you move not just through space, but through time too. Now here's where it gets really wild. If one end of the wormhole moves differently through time than the other, it could turn into a real-life time loop. You could enter one mouth and come out the other at a different time, either in the future or in the past. One way this could happen is by taking one mouth of the wormhole and moving it at near-light speed, kind of like dragging one end of a tunnel on a rocket ship. Thanks to special relativity, time for the moving mouth would slow down compared to the stationary mouth. When you brought them back together, the two ends would be out of sync. Step into the stationary end, and you could pop out of the moving end in the past, or vice versa. So, what determines whether you jump into the past or the future through a wormhole? It all depends on how the two ends are treated. If the traveling mouth experiences less time because of moving near light speed or hanging out near a massive object like a black hole, it could be younger than the stationary mouth. Walking through from the older end to the younger end would send you into the past. Going the other way would shoot you into the future. If you think about it like an escalator, one side is moving faster than the other. Depending on which direction you step, you either get ahead or fall behind. In a wormhole, stepping through the right way could get you to yesterday. Step the other way, and you land in tomorrow. But there's a catch. You can only go back as far as the moment the wormhole was first created. You can't use it to visit the age of dinosaurs unless the wormhole has been around that long. Most of the focus in science fiction is usually about going forward in time, because that seems easier. But going into the past is where things get really messy and interesting. Wormholes could, at least on paper, let you travel to your own past. You could, in theory, go back and meet your younger self. Of course, there are a few gigantic problems. First, wormholes would need something called exotic matter to stay open. Normal matter collapses under gravity. Exotic matter would have to have negative energy density, essentially pushing outward against gravity's pull and propping the tunnel open. No one has ever found exotic matter, but it's allowed by physics. Quantum effects show that negative energy can exist. We just don't know if it can exist in the right amount or be stable enough to use. Second, the wormhole needs to be kept stable. Even tiny disturbances, like radiation, particles, or tidal forces, could cause it to collapse before anyone makes it through. If the wormhole pinches shut while you're halfway through, it's not a pleasant outcome. Third, paradoxes start to creep in. If you can go back in time through a wormhole, you could do things like prevent your grandparents from meeting, or send yourself a message that changes your own decisions. Still, from a pure physics standpoint, wormholes don't automatically forbid time travel. General relativity allows solutions where closed time-like curves, paths that loop back on themselves, can exist. This means, under the right extreme conditions, the universe might let you travel to the past without instantly blowing up reality. Some physicists have tried to imagine how this could actually work. Kip Thorne, who advised on the movie Interstellar, famously studied how wormholes could be used for time travel. His work showed that if you had the technology to manipulate a wormhole, you could set up a time machine without breaking the known laws of physics. But the energy and control required would be beyond anything humanity can do right now. If traversing a wormhole sounds impossible for now, there's another strange idea lurking inside Einstein's man, something called a closed time warp curve, or CTC for short. And CTCs are even weirder because you don't necessarily want to wormhole. certain conditions would need to be met. First, the space-time through which the CTC would form must be extremely curved or warped. This could happen around objects like rotating black holes, also known as Kerr black holes. The immense gravity around such objects could create the kinds of closed time-like curves described by the equations of general relativity. In theory, if you were to enter such a black hole, you could follow the curve of space-time and loop back in time to a point before you entered. However, this is purely theoretical, and no one has ever observed such a phenomenon in practice. But time travel doesn't always need giant machines or massive black holes. Sometimes, the secret might be hiding in the tiniest things in the universe. In the quantum world, particles are strange little creatures. They can pop in and out of existence, act like waves, and even be in two places at once. One of the wildest things they can do is borrow energy they don't actually have, just for a split second, as long as they pay it back quickly. This lets them do things they shouldn't be able to, like tunneling through walls, or maybe even hopping backward through time for a blink. This idea comes from quantum field theory, a type of physics that combines Einstein's special relativity with quantum mechanics.